This video shows you how to construct a harmonic conjugate for a harmonic function. And if you recall, harmonic functions are solutions to Laplace's equations. And if you have a complex analytic function, the real and imaginary parts are both harmonic, and they're called harmonic conjugates. So if you start out with a harmonic function, can you construct a harmonic conjugate? And the answer is sometimes you can. This video will show you how. Before we get there, though, we need a tool from multivariable calculus. That tool is Green's theorem. And just to remind you what Green's theorem says, it says if I have two functions, p and q, both of them are functions of x and y being both real numbers, then the area integral is an integral over dx dy is equal to a line integral around the boundary, and with this particular choice of integrands. The picture that goes with Green's theorem is always helpful, and is also helpful in our case. If I have x and y, and I have some region D, some simply connected region D, then the boundary of D goes around the outside of it, like so. Now, the version of Green's theorem we're going to use is the one in which I'm going to imagine that this boundary of D is split up into two pieces, starting at a point x naught, y naught, and traversing this boundary to a point x, y, and I'll call this C1. And I could traverse this other one, I do it in green, so the other part of the boundary in the opposite direction, and I'll call this C2. If in fact I happen to know something about p and q, in particular, if I happen to know that the integrand of the area integral is 0, then it means that these two path integrals, those on C1 and C2, are equal. Let's derive that. So if, let me grab this guy here, if these two partial derivatives are equal, well, then that means the area integral that shows up in Green's theorem is equal to 0. On the other hand, using the other side of Green's theorem, that's the boundary of D. This is p, x and y, dx plus q, x and y, dy. I can write this as two separate integrals. One in which the orientation of the boundary of D agrees, that's the C1, and one where it does not agree. That's with C2. Of course, moving the C2 integral over to the other side, that means that these two integrals are equal. So these two integrals are equal. That means, in particular, that integration is independent of path. And that should feel very, very similar to the situation in which we have an analytic function. An analytic function, we know if we've got an analytic function, then it has an antiderivative. So similarly here, this works very much like antiderivatives existing, even though antiderivatives don't really make too much sense in this context. So this is analogous. It's analogous to an analyticity's independence of path property. Okay, now with that preliminary aside, dealing with Green's theorem, and this particular condition, which I'm going to box here, now we can proceed a bit to talk about how to construct a harmonic conjugate. So suppose I have a harmonic function. And let's let it be harmonic in a simply connected open set D. Very much like the Green's theorem situation that we just dealt with, because we're going to make use of that Green's theorem. So the proposition that we're going to prove by construction here is then there is a harmonic V, another harmonic function, such that these guys are harmonic conjugates. And caution is in order here. Is a harmonic conjugate is not symmetric. Which is to say that if V is a harmonic conjugate of U, it's probably not the case that U is a harmonic conjugate of V. You can't just switch real and imaginary parts of an analytic function to come up with some other analytic function. Okay, with that little caveat aside, let's now set about our task. So, because U is harmonic, it means the following equation is true. This is Laplace's equation. And put another way, these two are equal, but not exactly equal. It's equal with a minus sign. Okay, now with that minus sign in hand, that equation, of course, is the same. Let me unpack this slightly, because remember what I've got here in the formulation of Green's theorem is I have two separate functions, one p and one q. Here I've only got one function floating around, that being u. Let me sort of unpack them a little bit. Let me unpack them slightly. Oops, did that wrong. There we go. Again, I haven't done anything really. except for the fact that I have. Because now what I've exposed is I've exposed two different functions in the parentheses that are related to one another, of course, but they're actually, if you look at it, this is exactly the same format as the blue boxed equation. That means, in particular, I should think of this function, the partial derivative of u with respect to x, as q of x, y. And I should think of this boxed equation here, I should think of that as p of x and y. So just going up there again, I'm making sure that this blue boxed equation now holds. So by construction, this equation now holds. So in particular, because my domain is simply connected, integration along paths of path integrals p dx q dy is now path independent. So integral p xy dx plus q xy dy is now path independent, so long as the path stays in D. Because if I swap one path out for another, I'm essentially going to run this Green's theorem argument coming up with this kind of conclusion here. Okay, so given that, now let me use the following. Now let me pick a point. Let me select any point in D and just focus on that point and use it to define a new function. V of x and y. I'm going to define it as the path integral starting at x naught, y naught, this arbitrary point I've picked, and going to xy, to any other xy that lies in D. This integral that I'm going to write is I'm going to write down p and q. It's going to be path independent. So minus partial u y dx, that's the p. That's the y. So this definition is well defined because of this path independence. So because of this path independence, this formula for V is well defined. As in, I can write this down, and there's no ambiguity about the value of this function V at any point x and y. It's probably worth noting here that I've got too many x's and y's going on. Perhaps what I would want to do is make it a little bit clearer by saying that this is like a u of s and t and integrating with s and t. I'm not going to let that bother me terribly much at the moment. Okay, now if I start taking partial derivatives, though, now we kind of see that actually the claim is that this V is harmonic. So claim. So the claim is that V is harmonic. Put that definition again, and here I'm going to write it out with S's and T's. The first slot here is a y, so I'll call that t, and this is of s and t, ds. Oops. S and t, dt. Okay. So now if I want to take partial derivatives, then I want to see that this is harmonic. Now actually I don't have to take two partial derivatives, because in fact how I'm going to show this that u plus iv is analytic, because that implies that v is harmonic. Now in order to show that this is analytic, well, there's several ways you could do that. The quickest and most effective way at this case is just to show the Cauchy-Riemann equations. Okay, well, off we go. So I'm going to need to take partial derivatives of v and see how they relate to partial derivatives of u. Okay, so let me take partial derivative of v with respect to x. When I look at that, what's going to happen? Well, the partial derivative of v with respect to x is really the first component, i.e., this is really written out kind of like the fundamental theorem of calculus in a sense. In fact, it really is the fundamental theorem of calculus. And so the partial derivative of v with respect to x is really just this guy evaluated with s and t being x, y. Notice the t and the y line up. And what do you know? That is, in fact, the second Cauchy-Riemann equation. Now let's take a look at this other component. Again, the fundamental theorem of calculus is in play. And indeed, both of these are the Cauchy-Riemann equations. So that allows us to conclude that u plus iv is indeed analytic, and so v is harmonic. And in particular, v is then the harmonic conjugate of u. So the point being that this particular formula here that I've listed for v is in fact how you can build a harmonic conjugate. The conclusion being that this proposition, if I start out with a harmonic function in a simply connected open set, then it automatically has a harmonic conjugate. So that can always be done. If the domain's not simply connected, what can happen? What can go wrong? If the domain is not simply connected, then the problem is that v is no longer well defined. You could have potentially two different paths yielding two different points, and so this equation doesn't actually define a function. It defines a family of functions, and you have to pick one, and you can't.